All right. Hi, everyone. So we're going to be discussing the set 1 paper. Okay, the one that has all the questions number 1 to 4 from this particular set of questions. So we're going to begin. All right. So the SPM MRSM question. Diagram 1 shows a pastry chef decorating whipping cream on top of a cupcake by exerting pressure. Okay, I guess when you see liquid and you see that it has to do with pressure, you're probably thinking of Pascal's principle. Okay, so first question, what is the SI unit for pressure? You can answer Pascal or PA or Newton per meter squared. Okay, any one of these is probably is an acceptable answer. Okay, underline the correct statement in the bracket to complete the following sentence. The point at pressure X, okay, so this is Pascal's principle. Wherever the pressure in the liquid is, when you exert a certain force, you get the pressure. The pressure at all points, okay, is the same. So the pressure at point X is same as, okay, and since the question asks you to underline, okay, please underline. Okay, be precise about these kind of things lah. No, if people say underline, underline. Don't go and circle when it's so clearly stated underline. Okay, now based on the statement in 1B, state the physics principle evolved. As I said just now, this is Pascal's principle. Okay, now one application of Pascal's principle, as stated in 1C, Pascal's principle is anything to do with hydraulics. Okay, basically the word hydraulic only appears in Pascal's principle. Okay, so you're looking at the most obvious one is the hydraulic brakes. Okay, can also be hydraulic jack, can also be a hydraulic chair. Say, for example, like the dentist chair, it can go up and go down by itself. Okay, that's a hydraulic chair. Okay, so these are a couple of possible answers that you can use for this question. Okay. All right, the next question. Diagram 2 shows an object placed at 30 centimeters in front of a convex lens. Okay, and then the image. So obviously this is our object distance, okay, U. And then this part over here, which you can calculate for yourself, is the image distance, okay, V. So what is the meaning of real image? A real image is an image that can be captured on a screen. Okay, and since, sorry, let me write this again, screen. Okay, now since a real image is an image that can be captured on a screen, okay, this is just extra notes lah. Okay, a virtual image, okay, is the one that cannot be captured on the screen. So the definition is similar. Okay, one can be captured on the screen, one cannot be captured on the screen. Okay, so one is real, one is virtual. So not that difficult to remember lah. Okay, now based on diagram 2, determine the image distance. If the whole thing is 40 and that one is only 30, so obviously the image distance will be 10 cm. Okay, now then find the focal length of the convex lens. So whenever you see a lens question and you want to find the focal length or you want to find, the image distance, we always come back to the lens equation, which is 1 over f equals to 1 over u plus 1 over v. And the good thing about this is you don't have to convert the units. You can keep it in centimeters if you want. So you get 1 over f equals to 1 over 30 plus 1 over 10. Okay, now when you add this together, don't forget to flip it around. Okay, and you get the answer F equals to 7.5 centimeters. Okay, next question. If the lens in diagram 2 is replaced with a bigger diameter lens, state the change that occurs to the image. Okay, so when you have a bigger lens, okay, more light can enter into the lens. And so what happens is you will have a brighter image. Okay, brighter means dia lebih terang lah. You can see, it. This one, I wouldn't use the word sharper image because that not really very to do with diameter. Brighter lah, brighter. Why brighter? Okay, because more light can enter. Okay, the red color is the answer, the blue color is just extra notes for you to think about lah. When you think about bigger diameter lens, you can let more light enter, and so you have a brighter image. Okay, that's exactly what we want. All right, number 3. Diagram 3.1 shows a deflection tube. Now, the deflection tube only appears in one particular chapter, okay, which is electronics. And the deflection tube always has something to do with this concept, okay, or the process, which is called thermionic emission. Okay, so those are all key things that we need to remember. Okay, so thermionic emission. So over here, there's the cathode over here that that emits the electrons. It will be accelerated by the anode, and then after that it will be deflected, go up or down. Okay, so the process again is called thermionic emission. Now, when switch S1 and switch S2 are closed, while switch S3 is open, the electrons move towards the anode. Okay, let's take a look. So when S1 and S2 is closed, that means we sambung this one. Okay, and S3 is open, so the electrons over here will move towards the anode. Now that's normal. Okay, and this one is because it is already accelerated. Okay, this is the accelerating because of the extra high tension, the EHT lah. Okay, so the question is calculate the maximum velocity of the electron. Okay, so this one is very specific to the thermionic emission and also a little bit on the photoelectrons lah. But the formula is the energy of the electron, which is E times V, okay, equals to half mv squared. Okay, and you will use this to find the velocity. Okay, and again, this particular this particular formula or this particular equation appears only in this chapter or in this subtopic. Okay, so the value of E is given. Okay, 1.6 times 10 to the power negative 19. So you have 1.6 times 10 to the power negative 19 times. Okay, so what is the voltage given? You see the voltage given is 1.5 kilovolts. Remember, at this point, S3 is still open. Okay, so we're not interested in the 2 kilovolts. We're interested in the 1.5 kilovolts. So that's why we use 1,500. Okay, equals to half. The mass of the electron is given 9.11 times 10 negative 31. Then you write V squared. Okay, don't forget to square root and you will get the answer V equals to 2.295 times 10 to the power 7 meters per second. Okay, now diagram 3.2 shows the path of a cathode ray between deflection plates. Complete the path of the cathode ray. Okay, so obviously, since that electron is coming out here, okay, so all you need to do is, you know what? Sorry, let me write. Since the thing that is, that is going on the cathode ray are all electrons, because of thermionic emission. Okay, so obviously electrons are negatively charged, and so they will be attracted to the positive plate. Okay, so this is what's going to happen. You're going to get a deflection like this. Okay, as long as you can show that it's deflected. Okay, starting from this one. Okay, I guess I can make it a little bit nicer lah. Okay, draw straight lah. Okay, so straight and then deflect up. Okay, doesn't matter how you deflect lah. Deflect a little bit, deflect a lot. As long as you show that it deflects. Okay, that's the and deflects to the positive because it's an electron. So the question is, what happens to the path of the cathode ray when the value of EHT increases? Okay, so the reason why it's being pulled towards the positive is because there's a lot of voltage provided. And so this region up here becomes, in a sense, very, very positive. So it will pull the electrons very easily. And so if you provide a bigger EHT, okay, 3 kilovolts, 7 kilovolts, for example, okay, it will be even more positive and able to pull in the electrons a lot more. Okay, so we say that the deflection towards the positive plate. Okay, towards the positive plate is greater or more. Okay, it's more deflected lah, which means, let's say originally, dia punya deflection is just like that. Okay, more deflected means it will faster go towards the positive. Okay, so it'll be like really very fast to tarik lah. Okay, and the reason for this is the electric field is stronger. Okay, why is it stronger? Because the EHT has already increased. All right. Okay, question number 4 in this particular state. This is MRSM paper 2. Okay, so this is this seems to be a very common question. I've seen this in a few states, and it seems to be a very popular question among the states. So you have two satellites with different heights from the center of the Earth, sorry, from the surface of the Earth, okay, and they're orbiting. So obviously it's something to do with Kepler's third law. Okay, Kepler's third law is one of those laws that is so difficult because it's so many words and you cannot mistake it. Okay, so the square of the orbital period of any planet is directly proportional to the cube of radius of its orbit. Okay, so square of the orbital period, which is t squared, okay, and then this will be r cubed, which is actually in line with Kepler's third law punya formula lah. Okay, so just remember that. All right, so the height of the satellite M and the height of satellite N is given, okay, 3.6 times 10 7 and 2.0 times 10 7. Orbital period is 24 hours for M. Okay, so first of all, determine the radius of orbit. Now, the radius of orbit is the radius of the Earth, okay, from the center of the Earth to the satellite, from the center of the Earth to the satellite. So you don't want just the HN, you want to also add the R. Okay, so when you add 3.6 times 10 7 plus together with 6.7 6.37 times 10 to the power 6, your answer for M, okay, will be 4.237 times 10 to the power 7 meters. Okay, do the same thing for satellite N, but of course change this value, okay, and you will get the answer 2.637 times 10 to the power of 7 meters. Okay, so this is done to help you to remember. Okay, to remember that the radius of the orbit is not just the height from the surface of the Earth, but you have to add in together the radius of the Earth. Okay, and so when you substitute it into the formula, okay, t squared, t1 squared over r1 cubed equals to t2 squared over r2 cubed. The question is find the orbital period for the satellite N, which I'm going to assume is t2 lah. Okay, this is what we want to find. So the orbital period for M is given as 24 hours. Okay, so 24 squared over 4.237 times 10 to the power of 7 cubed. Where did we get this from? From this answer. Okay, and then equals to T2 squared, which is what we want to find, over 2.637 times 10 to the power of 7 cubed. Now, again, don't forget to, cube everything and make sure you calculate everything properly. And at the end of it, don't forget to square root because essentially the square is over here. You will need to square root in order to get your answer. So the answer is T2 equals to 11.784 hours. Okay, why do we use hours? Because the other time is given in hours. Okay, so this is quite a common calculation question that I've noticed in a few states lah. Okay, so it might be a good idea for you to study a little bit on Kepler's third law, especially the formula. Okay, let's continue. Question C, diagram 4.2 shows the motion of planet K orbiting around the sun. Okay, so point A and B, etc., etc. Now compare the distance traveled from A to B and C to D. Now this is a no-brainer. Okay, travel over here and travel over here. Okay, obviously A to B is more, okay, than C to D. Okay, either one lah. Okay, the distance traveled from A to B is bigger than the distance, up to you lah when you compare. Okay, now label in the box using X for the planet with maximum velocity and Y with minimum velocity. Now, I guess you can change the question to which side, which side, is it A, B, or C, D? Which side is going to go faster and which side is going to go slower? And so the tip for this is when it is nearer to the center of the orbit or the ellipse in that sense, which in this case is the sun. The nearer the Earth moves to the sun, it has to move faster, it has to orbit faster. Okay, so here will be X, okay, where the maximum velocity happens, and here this side will be Y. Okay, because it's so far away from the sun, so it moves slower. Okay, this one way to remember lah. It's a little bit crude, but yeah, you can remember it this way. The nearer we are to the sun, the faster we orbit. Okay, but the further we are away from the sun, the slower we orbit. Okay, and that's how we this one lah. And this is Kepler's second law. Well, technically, it's not really Kepler's second law lah. Kepler's second law is if let's say we have the sun, the center of the sun. So this, okay, this area and this area, okay, is the same. Okay, the sector is the same lah. Okay, so of course, explain your answer. Why is it that AB is faster than CD? Okay, so the answer will be the time for motion, okay, along AB and CD is the same. Okay, it takes an equal amount of time, okay, for AB to reach, for A to go to B and C to go to D. The time taken is the same. Okay, and so because AB is longer, okay, so AB is longer or further lah. Okay, so the velocity is higher. Okay, when I was looking at the marking scheme, they also provide this other alternative answer lah, which is you have a greater gravitational force. Okay, greater gravitational force at AB. Also acceptable. Since it's a 2-mark question, you probably want to go for 2 sentences. Okay, but the important thing lah, okay, is that since it sweeps out equal areas at equal times, okay, the time taken from here to go to here and here to go to here is the same amount of time. So obviously AB has to be faster and CD has to be slower. Okay, and so this is probably the key to this lah. And so why is it that AB is faster and CD is slower? Is because at AB there's a greater gravitational force. Okay, that's also one explanation for this. All right, let's move on to the next state, which is Kelantan. Okay, Kelantan question 1 to number 4. This is also another popular question that seems to be going around a lot of states lah. Okay, which is the photoelectric effect. Okay, diagram 1 shows light photons directed towards a metal surface. The photoelectrons are emitted from the metal. Okay, so what is meant by photon? Basically, photons are packets of energy. Okay, or packets of light energy, lah, I should say. Okay, packets of light energy, okay, with no mass. Okay, or you can also say a quantum of energy lah, also can. Okay, name the phenomenon involved. As I said just now, this is the photoelectric effect. Okay, photoelectrons will be emitted. Okay, so obviously you want to tick everybody, not tangkah. Okay, tick. So photoelectrons will be emitted from the metal when the frequency of light photons is more than the threshold frequency. Ngam at the threshold frequency also can, but this is either more or less. If it's less than the threshold frequency, I mean the word threshold okay, threshold is like the minimum frequency you need in order for you to have the photoelectric effect. So the next question, what happens to the maximum kinetic energy when the frequency of the light photons is increased? Okay, so this one we have to go back to the formula so Einstein's photoelectric equation is the photon energy equals to the work function plus the kinetic energy. Now the work function cannot change because the work function is how much how much energy you need to release the photons. Kinetic energy is, after the photons release, what are they just going to do? Stand around there and do nothing? No, right? They have to move lah. So the work function is, if the same metal is used, the work function is constant. Okay, so if you increase the frequency, okay, and since the photon energy is H times F, if the frequency increase, the energy increase. And so if the energy increase, the kinetic energy also will increase. Because whether you increase the energy or decrease the energy, the work function never changes. Okay, so the kinetic energy increases. Okay, which is the answer for number 1. Let's go to number 2. Diagram 2.1 shows a graph of radioactive decay of P with its half-life T half. Okay, and so what is the meaning of half-life? So my standard answer okay, the half-life is time taken for time taken for a radioactive substance. For a radioactive nuclei or nucleus, okay, to decay to half of its original or initial value. Okay, or somewhere along this line lah. Okay, half of the original radioactive nuclei to decay. Okay, to half of its original value. Of course, the key word is the word half lah. Okay, decay to half of the initial value. This one is a must, but must be in. No matter how you pushing lah. Okay, of course, time taken because it's the amount of time lah. But no matter how you pushing, these words must be in. Time taken, decay to half, original value. Okay, determine the half-life of T of radioactive P, show on the graph. So this is 2 marks answer. So we need to look at the original. Original is 2000. And so half of 2000 will be 1 will be 1000. Okay, and so you want to find the time it takes to go from 2000 to 1000. And so you need to draw the line and then go down. Okay, so it will be 10 days. Okay, 10 days. So 1 mark is given for the answer. And of course, 1 mark is given by showing it on the graph. Okay, again, everybody, during the real SPM, the paper will be a much nicer quality than our photostat paper lah. Okay, so even when you draw the lines, it will be very, very clearly seen. Okay, so don't worry. All right. Diagram 2.2 shows a curved graph, okay, of radioactive decay P and Q. Okay, and so these are now 2 different designs, but the initial activity or the initial number of nuclei is still 2000. So when you look at it, the time it takes to go to 1000 is different. For P, it takes 10 days, but for Q, it takes 5 days. Okay, this is probably what they want you to compare. So which radioactive has a shorter life? Obviously, it is Q lah. Okay, because Q takes only 5 days to reach half. Okay, so Q has a shorter half-life. Okay, and so what is the relationship between half-life and decay rate? Is the bigger the half-life, okay, the smaller the decay rate. Okay, it will be, in opposition with one another lah. So decay rate, the word decay rate actually refers to how fast the nucleus or the nuclei decays. Okay, in a sense I mean, there's a proper definition for it, but let's just put it simply. The decay rate is how fast the nuclei decays. And since the half-life is bigger for P, it takes a longer time to decay. So the decay rate will be smaller. Okay, so that's how we will understand the word decay rate lah. Okay, how fast it decays. All right, number 3. Diagram 3.1 shows a blue light wave passing through a narrow sickle slit. Okay, and so if it is a single slit, then we are talking about the wave phenomenon of diffraction. Okay, why? Because it's a single slit. If it is a double slit, then it's the interference. Okay, if this is a double slit lah. But our slit is only one only, so it's obviously diffraction. Okay, now diagram 3.2 shows the wave pattern, etc., etc. So of course the answer, the question will be draw the wave pattern after passing the slit. Now the most important thing about diffraction is that the wavelength doesn't change. Okay, so the wavelength is constant in diffraction. That means when you draw, you need to make sure that the distance between the two wavefronts is still the same as before diffraction happens. Now we know that when it passes through the slit, it's going to change direction, it's going to spread out. And so the wavefront will be in circular. Okay, so it'll be like this. So you need to make sure that the distance is roughly about the same. Okay, roughly about the same as the original distance. Okay, over here. I know my drawing is a little bit off, but yeah, the understanding is that it needs to be roughly about the same. Okay, and to complete this, usually I will get students to, draw out the direction. Since there's these three lines over here, we want to draw where the three lines go. So number one here, number two still goes straight, and number three kind of goes out like that, just to show that it is spreading out. Okay, so the first mark will be for the diffraction pattern. Okay, diffraction pattern means you need to see the circular pattern. The second mark is the more important one. Okay, the second mark is for the same wavelength. Okay, so you need to be very careful about drawing diffraction patterns because they're looking for that. Okay, the same wavelength. Yeah, they're probably not going to, measure and then, oh, this one is 2 cm, so you measure everyone that you draw. But like a very obvious wrong answer, okay, a very obvious wrong answer. Let's say this is the slit. Okay, a very obvious wrong answer will be if you just simply draw and then, yang penting dia keluar macam ni lah. But the wavelength is so near to one another. This is very obviously wrong. You will only get 1 mark for this. For this answer, you only get 1 mark because the pattern is there. The circular pattern is there and it's spread out. Okay, but in terms of the wavelength, out. Okay, which is a waste because this is a very simple drawing. All you have to remember is that after diffraction happens, wavelength doesn't change. Okay, so you need to make sure your drawing also reflects that. Now, the wavelength of blue light is 500 nanometers and the speed of light is 3 times 10 to the power 8. Calculate the frequency. Whenever you have a wave question, usually we will always end up using the wave equation, almost certainly. Okay, now the speed of light is given as 3 times 10 to the power 8 equals to the frequency we want to find. Now look at the unit, people. 500 nanometers means you need to change it back to meters, which is 500 times 10 to the power of -9. Okay, and so you get F equals to 6 times 10 to the power of 14. Don't forget the unit of frequency, which is hertz. All right, and so lastly, what happens to the wave pattern formed on the screen when the bigger size of the slit is used? So right now, the slit is, pretty small in size lah. But what if I make it, a bigger slit? Like I make it even more far apart, like this. Dia bukan dekat macam ni, tapi dia jauh sudah macam ni. Okay, so this is one thing that will happen. Not one thing, the most obvious one. Okay, it will be a less obvious diffraction pattern. Okay, a less obvious diffraction pattern is observed. Okay, in our original case, this is a more obvious, very circular. Okay, a less obvious one will be, it looks almost exactly like. Okay, then last dia akan jadi macam ni. They will become, it looks almost exactly like the original, except bend a little bit at the side lah. Okay, at the side it will bend a little bit, but most of it still looks like the original. Okay, so much to say that diffraction pattern is very obvious when the size of the slit is very small. Okay, and so that's a very important characteristic when we talk about diffraction. Okay, 4.1. shows two metal plates X and Y connected to extra high tension supply. When the switch is turned on, a strong electric field is produced. Okay, etc., etc., etc. And so the question is, what is the meaning of an electric field? Okay, so the electric field is a region where an electric charge experiences an electric force. Okay. Now, another popular field question is a magnetic field. Okay, what is the meaning of a magnetic field? So I'm just going to write down here since we are talking about the field. So the magnetic field is almost the same definition as this. Okay, magnetic field is a region where an object, okay, experiences a magnetic force. Okay, so we're basically just substituting object and electric charge. Of course, electric with magnetic. Okay, so the what do you say? The words are almost the same. Okay, for electric and and magnetic field. Okay, it's just that when we talk about electric field, the one that experiences the electric force is obviously an electric charge lah. Okay, I have seen books that write object, but I'm not entirely very clear whether that will be an acceptable one or not lah. Okay, now the candle flame is left burning between two plates for 240 seconds, okay, and the current flow is 0.5 amps. Okay, and so calculate the amount of charge. Amount of charge refers to Q. Okay, and this is a formula Q equals to I times T. Everything is given for you is 0.5 times 240, which will give you 120 coulombs, okay, for the amount of charge. Now, the distance between two plates X and Y is 20 cm. Calculate the strength of the magnetic field. Now, the strength of the magnetic field is given as E equals to the voltage provided over the distance. Okay, the distance, but the distance has to be in meters. So, this one is 2 kilovolts. Okay, so if you change it to 2000, and our distance is 20 cm, so it's 0.2. And so you get 10,000 volt per meter. Now, this is a very rare occasion where we see this particular formula being used. It's not a very common question, this particular question. Okay, but so I like it. I appreciate that they came up with this question so that we can have an opportunity to discuss it. It's not very common, okay, but it's good to know as well. All right, explain how the candle flame pattern. So this is an explanation question. Usually will occur in question 4 and usually takes about 3 marks lah. Okay, and so this is probably one of the heavier sides of it lah. Okay, so let me show you the answer. Okay, so the answer is here. Okay, but basically what I want to explain is this lah. So the candle flame, what the candle flame does is, this candle flame. Okay, what it does is that it ionizes the air. Okay, so all the air around us, what the candle flame does is it turns the air into positive and negative ions. Okay, positive and negative ions, all around it will be positive, negative ions. Now, naturally, all the positive ions will be attracted towards this plate because the negative is here. And all the negative ions will be attracted towards this plate. Okay, because it's attracted to the positive. Now, if you remember your chemistry, you know that the positive ions are heavier compared to the electrons. Negative ions are just electrons which are very, very light. The positive ions are much, much heavier. And that's why this side of the flame that contains the positive ions, okay, will be very skewed. It's like, pushing a very heavy person to one side. Okay, so that's why more of the flame is concentrated towards the negative plate because the positive ions are heavier. The main thing that you have to mention is that the positive ions have a greater mass. Okay, this is probably the single most important reason. The positive ion has a greater mass, and so the candle will spread out more towards the positive ion side. Okay, you can pause the video and copy this answer down. All right, let's continue on to Pahang 2022. So once again, the same thing, okay, light and then electron. So this phenomenon is known as the photoelectric effect. Okay, so name the minimum frequency. The minimum frequency is called the threshold frequency. So what will happen to the kinetic energy of the electron when the intensity of the light increases? So if you remember the question just now the question is asking when the frequency increase. Frequency increase means energy increase, so kinetic energy increase. But now it's talking about the intensity. It means you shine a brighter light, but it's the same light. Okay, so the intensity of light doesn't change anything. Okay, it doesn't change the energy, it doesn't change the kinetic energy, so it remains unchanged. Okay, and so the reason for this is kinetic energy of electrons is only, okay, affected by frequency and not light intensity. Okay, so that's one very important thing to remember. All right, next question is a wave question. I guess it's a sound wave question. Or either a sound, no, it's electromagnetic wave because radio waves. Okay, so television broadcasting system. Okay, name one characteristic of radio wave. Now, there are many, many characteristics of radio wave because all you have to do is give the characteristic of an electromagnetic wave. Okay, there are many, 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 many characteristics of electromagnetic waves, and I would suggest that you look at them lah. Okay, but of course, I think the most famous one or the most normal one is that it can propagate in vacuum. Okay, or does not need a medium to propagate. Okay, these are probably the two most famous, but there's so many. It travels at the speed of light. It's a transverse wave, it's so many lah. Okay, now the frequency of the radio wave is 2.5 times, sorry, there's a mistake here, 10 to the power 8. Calculate the wavelength of the radio wave. So obviously, when you talk about electromagnetic waves, you have to remember that the speed of the wave is the speed of light, 3 times 10 to the power 8 meters per second. If you don't remember this, then you cannot answer this question because you'll be like, oh, I don't have enough information. Actually, you do, you just have to remember it. Okay, so V equals to F lambda. You substitute 3 times 10 to the power 8 equals to 2.5 times 10 to the power 8. Then you find lambda. You get lambda equals to 1.2 meters. Okay. Now name the wave phenomenon that is involved. Okay, so radio wave, whenever you see blocked by hills or tall buildings, but you can still receive. So this is obviously a diffraction because you have obstacle. Okay, so the name wave phenomenon involved is obstacle. Okay, and so you can say why it can happen is the waves are spread out, okay, after passing through an obstacle. And in this case, the obstacle is the hill or building. Okay, so the waves are spread out and still it can reach the receiver. Okay, although it is very, very spread out. Okay, let's go on to the next question. Okay, once again, it's Kepler's second law. Okay, this particular question. Now, once you see an ellipse and two areas, you kind of know that this is Kepler's second law. Okay, which is also known as the law of areas. Okay, remember the first one is the law of orbit. The second one is the law of areas. And the third one is the law of, I think it's the law of periods. Okay, if I'm not mistaken, if there's a mistake, please put a comment in the video. Okay, so again, the linear speed from P to Q is more than R to S or less than R to S. So remember, the nearer you are to the sun, the speed is much bigger. Okay, so take this answer. So again, you can give the same reason as the one that you gave just now. Distance of P to Q, okay, is greater than distance of RS, but time is the same. Okay, very similar to the question that we saw just now, lah. Okay, calculate the orbital period. Okay, now this is a little bit different. They're not using the law of periods, okay, which is the third one, but they're asking you to calculate the orbital period and look at the information given. They're given you the mass of the sun. Okay, and so we use a very rarely used formula, which is T squared equals to 4 pi squared over GM RQ. Okay, this is a very, very rare question. Okay, because of, it's so complicated, so many things you have to put in. Okay, now the average distance from the center to the sun is 1.5 times 10 to the power 11. So this is the R. You want to find the T. Okay, G and M is given in, in the formula list. So substitute it correctly. I'm not going to show the calculation here, but substitute it correctly. Just remember that this is R. Okay, 1.5 times 10 to the power 11 is R. The mass of the sun obviously is the big M lah. Okay, the center of the elliptical orbit. Okay, and so once you square root the T, you should be able to get T equals to 3.17 times 10 to the power 7 seconds. Okay, the standard answer is seconds, but if you want to change it to hours, then you divide by, you divide by 24 and 60 and 60 lah. Okay, change the second to hours. So you get about 8800.85 hours. Okay, either one is fine lah, because you're not expected to, give it in hours. If you leave it in seconds also is fine, especially after such a long calculation after this. Okay, it's a very long calculation, okay, that you need to be very, very careful of lah. Okay, the instrument which is used to measure the gas pressure, this instrument is called a manometer. Okay, it is in the shape of a U. Okay, the original YouTube lah. Okay, if you're my student, you will know lah. I will always say this is the original YouTube, not the YouTube that you're watching this video in now. But the original YouTube is also known as a manometer. We rarely use the word YouTube lah. Okay, we prefer you use the word manometer. Okay, compare the gas pressure in the flask here and the atmospheric pressure. Now, if this is a tug of war, and the gas pressure is pushing here and the atmospheric pressure is pushing here, it's very obvious who is winning. The one that is winning is the gas pressure, because it's able to push up more than the atmospheric pressure can push up. Okay, so the gas pressure is greater than the atmospheric pressure. Okay, and so state the difference in the gas pressure, atmospheric pressure in meters H2O. So you see the 36 centimeter. This is the difference lah. Okay, but it's in centimeter, and it is in water which is H2O lah. Okay, so you need to change the 36 centimeters to 0.36 meters water. Okay, and in case you have forgotten, this is a unit for pressure. Okay, the whole thing, just like centimeter mercury. Okay, but we're not using mercury. In our diagram here, we're using water. So we have to change it to meter water. Okay, and so calculate the gas pressure in meter water. So the gas pressure, okay, is the difference, which is 0.36 plus the atmospheric pressure, 10.3 meters. Meter water. Okay, which will give you 10.66 meter water. Okay, now how do you figure this out? Basically, okay, you need to talk about the difference lah. Okay, so how is the difference happening? It is because of the gas minus the atmospheric pressure. Okay, the gas pressure minus the atmospheric pressure gives you that difference, and the difference is 36 centimeters or 0.36. Okay, and so when you move it around, when you move around this formula, you will get that the gas pressure is equals to the difference plus the atmospheric pressure, which is what I used to do this. Okay, the difference plus the atmospheric pressure. Okay, and so this particular formula is not set on, dia bergantung kepada siapa yang menang. If the gas pressure is winning, the difference equals to gas minus ATM. But if the atmospheric pressure is winning, it will look like this lah. Okay, it will look like this. So the difference in pressure is now greater on the atmospheric pressure side. So in this case, the difference will be the atmospheric pressure minus the gas pressure. So don't think that whatever that I wrote here is set in stone. This is only in this situation where the gas pressure is winning in that sense. If the atmospheric pressure is winning, the difference is caused by the atmospheric minus the gas. In both instances, the beginning is the same, which is the D. Okay, now based on your answer in 4C2, which is this, the 10.66, okay, determine the the atmospheric pressure in Pascal. Okay, in Pascal. Sorry, there's a mistake in this question because the Malay one says tekanan gas, but the English one says atmospheric pressure. So I'm going to change this to gas pressure. Okay, calculate the gas pressure in Pascal. Now, when you want to change from meter water or from centimeter mercury to Pascal, you use the formula P pressure equals to rho GH. Density times gravity times the height. And the height is actually the pressure, the one that you count just now, 10.66. Okay, so rho is 1000. G is 9.81 and the H is 10.66 meters. Good news is it's already in meters, so you don't have to worry. And so your final answer will be 104,575 Pascal. Okay, you can leave your answer as such. Now, what happens? Water in the instrument in diagram 4 is replaced with mercury. So we replace water with mercury. What happens to the difference in liquid levels? The difference will decrease. Okay, it is harder to achieve such a big difference mainly because we can say that mercury is a heavier liquid compared to water. Water is very easy to push around, but mercury is very hard to push around because it's heavier in a sense. Okay, but we don't say heavy, we don't really say heavy mercury Okay, so the difference will decrease. There will be a smaller difference, and the reason for this is because the density okay, the density of mercury is higher. Okay, compared to water, density of mercury is much higher. All right, we're halfway through. Let's go on to the fourth paper, okay, which is the SBP paper. Now, diagram 1 shows a slinky spring that demonstrates a type of wave, okay, JKLMNOP. So what is the type of wave? Because it's not going up and down, it is a compression rarefaction. So we are obviously talking about longitudinal wave. Okay, another possible answer, since it's only asking for type of wave, is a mechanical wave. Okay, I think both answers should be accepted because they're not really specifically asking for a certain type. Okay, they are asked, so both answers will be accepted. Now, in longitudinal waves, this part where the spring is nearer to one another, okay, is what we call a compression region. Manakala, this part, which is a lot more open, okay, this is called a rarefaction. And so this question is K. K is a region of rarefaction. Okay, now circle 2 letters that represent a wavelength. Wavelength is from one compression to the next compression, or one rarefaction to the next rarefaction. So there are many possible answers for this. Okay, if you take a look, it can be, but again, the question is asking circle 2 letters only. Don't go and circle every letter. Either you circle J or L, okay, or you circle K and M, or you circle L and N. There's so many okay, or you can circle M and O, or the final one is you can circle N and P. Okay, it must be one after another okay. And so one example of a wave, longitudinal, very obvious, this is a sound wave. Okay, there's only one wave that, I mean, at least in our level, there's only one wave that is longitudinal. Okay, diagram 2 shows an alpha decay equation. Very interesting equation because they already give you the energy at the end. So what type of charge is an alpha particle? An alpha particle is a positive charge. Okay, now calculate the mass defect. So this is E equals to mc squared, but they're asking for the mass defect in AMU, not in kilogram. When you calculate using the joule for energy, okay, that particular mass will be in kilograms. Okay, so you need to be wary of this lah. So 6.4848 times 10 to the power of negative 13. Okay, equals to m, which is what we want to find, 3 times 10 to the power 8, the whole thing squared. Don't forget to square it. Okay, once you divide it, you'll get m equals to 7.61 times 10 to the power negative 30 kilograms. Okay, and then how do you change from kilogram to AMU? Is you divide by this number, 1.66 times 10 negative 27. And so you will get 4.58 times 10 to the power negative 3 AMU. Okay, as a reminder, how to do from here to here is you divide by 1.66 times 10 to the power negative 27. Okay, always remember this. Of course, from AMU to kilogram is easier, multiply. Okay, kilogram to AMU, not bad. It's not a very commonly asked question. Okay, now if the mass of defect increases, what happens to the energy? This is very obvious. From the formula, so you know. Okay, if the mass defect increases, the energy also will increase. Okay, once again, I want to take this opportunity to remind all of you, if you see the question, what happens or what will happen, generally, okay, the answers are either one of the three. Either it will increase, or it will decrease, or it will remain unchanged. Okay, so this is a very important keyword, especially if you don't know what is the answer. Okay, then you know that the answer is one of the three. Just give it a shot. You never know if you will get it correct. Diagram 3 shows the velocity time graph of a car moving in linear motion. Okay, and so the velocity is over here. So state the meaning of velocity. Meaning of velocity is rate of change of displacement. Okay, now state the type of motion of the car. Now, whenever we see the words state the type of motion, you either need to be talking about the velocity and or the acceleration. Okay, don't say the car is moving. Oh, wow. Okay, or don't talk about the car's position. Type of motion, generally, okay, type of motion refers to, you can talk either about the acceleration or you can talk either about the velocity. Okay, now in this case, very obvious that the velocity is increasing, and since it is a straight line, it is a constant acceleration. You can write both, okay, or you can write one. It's only one mark anyway. Okay, so it's either constant acceleration because the graph is a straight line, or increasing velocity. Either one of these answers, I think it's fine. Okay, honestly, I think it's fine. Okay, momentum of the car, the mass of the car is 1200. During its move with constant velocity refers to this section. So it's saying that the velocity is 10 and the mass is 1200. So the momentum equals to mass times velocity, 1200 times 10 will give you 12,000. The unit is kilogram meters per second. This is a very easy question. Yeah, especially if you know what is the formula for momentum. Now sketch the acceleration time graph for the motion of the car. Okay, so in the first 10 seconds, as we said just now, since it's a straight line, the acceleration is constant. There is a value and it's not zero and it's constant. But in the next 15 seconds over here, the velocity remains the same. Now, if the velocity remains the same, means no acceleration. No acceleration means zero. Now, constant acceleration is not the same as zero acceleration. Okay, it's not the same. Zero acceleration is no acceleration. Constant acceleration means there's a value to it. And so because there's a value, okay, you need to draw from 0 to 10, there's a value. And then from 10 to 25, the acceleration is 0. Okay, and so this one usually we will connect with dotted lines, okay, to show that there's some sort of continuity lah. Okay, but the question is, I need to know what is this number at the side here. And so how do we count the acceleration? We have to go back to the graph. Okay, acceleration is the gradient of the graph. So 10 divided by 10 is 1. Okay, 1 meters per second squared. So you will have to write the number 1 here. Okay, remember in this graph, the acceleration is determined by using the gradient. So you find the gradient of this line, you will get 1, and so you substitute the number 1 into the graph. Okay. All right, next question is from heat. Okay, diagram 4 shows an electric steamer. What is the meaning of the specific latent heat of vaporization? Okay, now there's two types of latent heat, if you remember. Fusion is talking about solid to liquid. Okay, but vaporization is talking about liquid to gas. So whatever words that you put in, you need to make sure that you're putting in the correct the correct state of matter. Is it going from solid to liquid, or is it going from liquid to gas? And the keyword vaporization will tell you how to put the definition correctly. So it is the heat required, okay, to change. And this is a very important word, 1 kilogram. The word specific, because of the word specific, you have to put the word 1 kilogram. Okay, heat required to change 1 kilogram of liquid to gas. And the next important word is with no change in temperature. Okay, with no change in temperature. Sorry, my writing. Okay, no change in temperature, then liquid to gas because it's vaporization. So with fusion, it'll be the same thing, except that instead of saying liquid and gas, okay, you will change a solid to liquid. Okay, that's the specific latent heat of fusion. Now, the water in the steamer of 0.5 kilograms with an initial temperature of 25 is heated until it boils. Okay, so boils will be 100 degrees Celsius. So the change of water temperature will be 100 minus 25, which will give you 75 degrees Celsius. This is no-brainer, as long as you remember that water boils at 100 degrees Celsius. Okay, calculate the quantity of heat required. Okay, so this one is not talking about latent heat yet. Okay, we're talking about the specific heat capacity of water. So Q equals to mc delta theta. M, the mass is given as 0.5. The specific heat capacity is 4,200, and delta theta you counted as 75. So you will get 1.575 times 10 to the power of 5 joules. Okay. Now, the food in the steamer requires 4.8 times 10 to the power 5 of joules of heat to be steamed. Okay, so the heat that you need to steam is 4.8 times 10 to the power 5. So calculate the mass of the steam produced. And now they give you specific latent heat. So this is a Q equals to mL formula. L is the latent heat. Okay, so 4.8 times 10 to the power 5 equals to M times 2.26 times 10 to the power 6. And so you calculate, you get M equals to 0.212 kilograms of steam, which is quite a lot if you think about it. 200 grams of steam is no joke. Now, of course, question number 4 is usually where the first explanation question comes. Okay, so we need to be prepared for this. Explain how food is cooked with an electric steamer. Okay, ta-da! Okay, so first of all, water boils to produce steam. Okay, the main important thing about electric steamer is that it needs to produce steam, and the steam is the one that cooks the food. Now, how does the steam cook the food is by means of condensation. When condensation happens, steam turns into water. Okay, and in doing so, it releases a lot of heat because it needs to release heat in order to condensate. And so the heat is released in the form of latent heat of vaporization onto the food. And that heat that is released will cook the food. Okay, so that is how an electric steamer works. And so you would probably want to use this opportunity to pause this video and copy down this answer lah. All right, let's move on to Kedah 2022. Okay, once again, okay, we see this question. Okay, but at this point, I think even I am bored of answering this question because we answered so many times now. But you know, the point of answering is to keep practicing so that we don't get the answer wrong lah. Okay, Kepler's second law. Kepler's second law is a line that connects a planet to the sun. Okay, sweeps out equal areas at equal times. Okay, which is why I keep saying that the time taken from here to here and the time taken from here to here is the same, precisely because this area is the same as this area. Okay, so the time is the same, and that's Kepler's second law, equal areas at equal times. Shape of the orbit of the planet is always elliptical, never a circle, because an ellipse has two focal points. Okay, what will happen to the velocity of the planet when it moves apart from the sun? Okay, this is a very strange question. I'm not really sure whether it's talking about the velocity here, okay, away from the sun, means at CD. I think so, but the way the question is worded is a little bit strange to me. At first, I thought it was talking about like escape velocity or something, but I guess it's referring to the particular part in CD, okay, as it moves further from the sun. So of course the velocity will decrease, we know that it has to move slower. Okay, and so we will say that the velocity will decrease because it takes a longer time. Okay, it takes a longer time to complete one sector of orbit, which is that particular small sector, okay, around the sun. Okay, the smaller sector, the part that's away from the sun, that particular sector, it takes a longer time. Well, it's a shorter distance, but it takes the same amount of time as the long distance. The long distance. Okay. Question number 2. Diagram 2 shows the decay curve of a radioactive substance X. The activity of a radioactive substance X was measured by a Geiger-Miller tube, etc., etc. So we have another half-life question again. Okay, and so at this point, I'm not even going to bother to write the answer here because you can find it in the few minutes ago. Okay, so write down the meaning of half-life on your own. Okay, for this. So determine the half-life of radioactive substance X. Now, as opposed to the question just now, which was 2 marks, they ask you to show on the graph, right? This one you don't have to show, but it's always good to show either way. Original is 800, so half will be 400. If we draw a dotted line, it will be somewhere here. Okay, so this will be about 5, what's the unit? Minutes. Okay, 5 minutes. Now, what percentage remains undecayed after 15 minutes? So you need to know, okay, when you talk about percentage, initial value is 100%, always. Although I know this graph says 800, but 800 is activity. They're not asking for activity, they're asking for percentage. So if they're asking for percentage, you start with 100. If you're asking for activity, okay, then you use whatever activity that is given in the question. In this case, it will be 800. Another possible one is, what is the fraction? Okay, if they ask you for fraction, or if they give you a fraction, you need to write 1. Okay, 1. You start with 1. 1 is the initial. So 1, then becomes half, then becomes quarter, etc., etc. But since percentage, we start with 100%. After 5 minutes, which is 1 half-life, it becomes 50%. After another 5 minutes, which is 10 minutes, Okay, it becomes 25%. And after 15 minutes, after 3 half-lives, you get 12.5%. How did I get this? All I did was just divide by 2, divide by 2, divide by 2. Okay, you can actually leave the answer like this to get the full 2 marks. Okay, totally not a problem at all. Now, give a reason why the readings of the rate meter did not drop to 0. So, notice that whatever half-life graph that you get, okay, it will never ever touch the x-axis. It will always be, we call this an exponential graph. Okay, it will always be nearing 0 but never 0. Why? Because there is such a thing as background radiation. Okay, and background radiation is radiation that comes in all forms all around us, from the sun, from the rocks, from your table, from your computer, from your phone. Okay, but very, very, very small value. Okay, and so it's not as hebat as this 800 activity, no lah. Okay, very, very small value along the lines of 0 point something. Okay, very, very small value. But we call all this background radiation, and which is why we can never really be totally radiation free. Okay, all around us is radiation. I bet you're watching this using Wi-Fi. Yes, Wi-Fi also is a form of radiation, okay, in a sense. All right. Okay, once again, quantum physics. So maximum kinetic energy EK varies with the frequency F of an electromagnetic ray. Okay, on diagram 3, mark X at the value of the threshold frequency. Now remember, threshold frequency happens, no, sorry. The threshold frequency is the frequency in which the kinetic energy is 0. Okay, because the photon energy, okay, if there is no kinetic energy, all the energy has been converted into just releasing the electrons. Haven't even make the electrons move, just releasing them. Okay, so you want to mark X over here, right at 8 times 10 to the power of 4 Hertz. Okay, that's the threshold frequency. Now, explain how electrical energy is produced by the solar cell. It's quite easy. Basically, it's just asking you to talk about the photoelectric effect. Okay, so the light shines, okay, on the solar cell to emit electrons. Okay, and this one, in case you don't know, this is called the photoelectric effect. Okay, second point is, of course, if the electrons are just emitted by they're standing there doing nothing, no point lah. Okay, so the electrons are stored in the solar cell as electrical energy. Okay, and that's how electrical energy is produced by the solar cell. Okay, calculate the work function. Remember, the work function is almost the same as energy. So energy is HF, but the work function is the energy at the threshold frequency, so HF naught. And since you already determined that the F naught is 8 times 10 to the power of 4, and H is given as 6.63 times 10 to the power of negative 34, the F naught is 8 times 10 to the power of 4, you will get the answer 5.304 times 10 to the power of negative 17 joules. Sorry, my bad. It should be times 10 to the power of negative 29. Okay, negative 29 joules. Okay, fourth one. Diagram 4 shows a traffic light with mass 20 kilograms hanging with 2 cables between 2 walls. So what is meant by forces in equilibrium? Forces in equilibrium basically means that the resultant force, okay, is 0. If you write it as simple as this, also it should be accepted, 0 newtons. Okay, the resultant force acting on the resultant force from all the forces acting on the object is equals to 0. Okay, that's what it's meant by forces in equilibrium. Now, draw a triangle of forces that acts on a traffic light. So obviously one force down here, which is the weight. Okay, that's the down one. And then you have the two that is, one this side and one this side. That's the tension lah. Okay, and since there's 20 degrees in between the two of them, okay, this particular angle and this angle will be the one that's important. And so, this angle is how much? 70 degrees. This is also 70 degrees because when I join this, is 90. Here is 90. And why is this 70 important? Because when we draw, we need to make sure that the three lines follow one after another. So usually I tend to start with the weight. Okay, this is the weight downwards. And then after that, I will go to the left. Okay, this is the first tension. And then the second one is to the right. Okay, to the right tension. We have to make sure that all three of the arrows are following one after another. Okay, they're all moving in one direction. This is a situation where the forces are in equilibrium. But it is not enough to write just the forces. You need to give the angle between the forces, which is why I said, I emphasize this quite important lah. Okay, so this one is 70 degrees, which follows this particular one. Okay, this particular, look at that shape over there. Yeah. Okay, and this one, this one over here, okay, is also 70 degrees. Since they are both the same tension. And so you get a final angle over here of 40 degrees. Okay, and so this is how you would draw the triangle of forces. You need to include the forces and the names and the arrows, and also the angle, okay, between each force. Now, if the traffic light is in equilibrium, calculate the weight. Okay, this is very easy. You are given that the traffic light is 20 kilograms. So the weight will be 20 times 9.81, which is 196.2 newtons. Okay. Now the tension of each string, is you need to count the vertical component because the weight is down, and so the vertical component of this 70 lah. Okay, let me rub this off to show you. Okay, so this one is here. Okay, this particular tension here, the vertical one is here. Manakala, this particular tension over here, the vertical one is here. Okay, and so this is the resolution of forces. Okay, and so you know that since the 20 is touching the horizontal component, okay, so this one will be T cos 20, and therefore this one is T sine 20. Likewise, the same thing over here, this component is T cos 20, but we're not interested in the left-right component. Why? Because the balance is up and down. So you need to find the up component. The up component will be T sine 20. That means this T sine 20 plus this T sine 20 is equals to the weight. Okay, the two T sine 20 is equal to the weight. So 2 T sine 20 is equals to the weight, which is 196.2. And we use this to find the value of T. Okay, you'll get T equals to 286.83 newtons. Okay, so this is this is one of the more complicated calculations lah. Okay, in physics form 5. Physics form 5 got a lot of weird calculations now. Electricity is also another one that I know a lot of you don't like. Okay, this is of course the other one lah. Now, if the horizontal angle between the cable and the traffic light increase, which means if I increase this 20 to a bigger value lah, okay, so what will happen to the cable tension? Of course, the cable tension will decrease. Okay, it will start to be looser because you're bringing it up lah. All right, the final state. Okay, we are down to our last 4 questions. So, Terengganu 2022, this question 1 to 4. Diagram 1 shows the reaction equation in a radioactive decay process that produces X particles. Okay, and so what is the meaning of radioactive decay? So, radioactive decay is a process, okay, where an unstable nucleus becomes more stable by emitting radioactive radiation. Okay, keywords is unstable become more stable. And how does it do it? By emitting radioactive radiation. Okay, so these are the keywords for this particular definition. Okay, what is the type of decay? Now, if you take a look here, the 6 become 2, so here is 4. 88 become 86, so here is 2. 4,2 is a 4,2 helium, which is the answer for question number 2 lah. Okay, 4,2 helium. Okay, so the type of decay is an alpha decay. Okay, or you can also fully spell it out lah, okay, if you want. Now, why does a radioactive substance decay? Basically, radioactive substances decay to become more stable. That's it. Okay. All radioactive substances decay because they only have one purpose, which is to become stable. Okay, you want to go from unstable to become more stable. All right, diagram 2 shows a 5.5 times 10 to the power 2 kilogram mass, okay, etc., etc. Oh, this is centripetal force. Interesting. So what is the meaning of centripetal force? So centripetal force has a few keywords lah. Okay, it is a force on an object in circular motion. So this is the first keyword. Okay, the object must be in circular motion in order for it to experience centripetal force. Okay, and acts towards the center of the circle. Okay, again, this is the keywords. Acts towards the center of the circle. The definition for centripetal force. Now, of course, the question is, explain how the satellite can remain motion in a circular orbit. Okay, so this is the answer. So the satellite remains in motion in a circular orbit because of this thing called the centripetal force. But because it's a 2-mark question, we need to explain how that force is created. So it's created due to 2 things. Number 1, there's the gravitational force between the satellite and the Earth, okay, which is Newton's universal law of gravitation. Okay, there are 2 objects and they are always have this force, attractive force with one another. So gravitational force between the satellite and the Earth combined with the gravitational acceleration of the Earth, okay, that acts towards the center, okay, keeps it in its circular motion and gives that centripetal force to the satellite. Okay, you can pause the video to copy down this answer lah. Okay, calculate the centripetal force. The formula is F equals to mv squared over r. Okay, so m is 500. V is 6960 squared over R is 8.3 times 10 to the power 6. Okay, all this information is given in this one. 500 is 5 times 10 to the power 2. 8.3 is over here. And then 6960 is 6.96 times 10 to the power 3. Okay, so you will finally get the answer 2.92 times 10 to the power 3 newtons. All right. Question number 3. Diagram 3 shows a circuit with a transistor that acts as an automatic switch. Now, if you see the 2 lights over here, then you know that the resistor X is a light dependent resistor. Okay. Given the resistance of resistor X is 40 kilo ohms, okay, when it is dark. Okay. And the potential difference across TU over here is 1.2 volts. Okay, now always remember this, that in the transistor circuit, this voltage is the same as this voltage. So if this whole thing is 6 volts, you know that if this is 4.2, the voltage that's running across the 10 kilo ohms will be the balance, okay, which is 4.8 volts. Okay, so question is, what is the potential difference across TU? Obviously, there's a mistake in this question lah. Okay, this should be TS because they already gave TU. Why would they give? Sorry, my mistake. This should be ST, because the question is ST. Okay, so if this bottom here is if this top over here is 1.2, then the bottom is 4.8 volts. Okay, so this question is correct. Sorry, my bad. The Malay version is correct. So ST is 1.2 volts. And according to the voltage divider, the remaining voltage goes to the light dependent resistor. Okay, so the answer is 4.8 volts. So then you can use that to calculate the current that flows through resistor X by using Ohm's formula, V equals to IR. V is equals to 4.8. I is the one that you want to count, and this one is 4,000. Sorry, 40,000. Okay, 40,000 ohms. Okay, because it's 40 kilo ohms. Let me get this right now. Yeah, 40 kilo ohms. It's 40,000 lah. And that's a lot. Okay, 4.8 divided by 40,000 is 1.2 times 10 to the power of -4 amps. Okay, very, very small value, but small enough to light this one. So of course, the emitting diode has to be explained lah. Why is it that the emitting diode lights up when the resistor X is in the dark? Of all the transistor circuits, the light dependent resistor is one of the more famous ones. Okay, but the explanation now, whether it is light dependent resistor or the other one, which is the heat dependent or the thermistor, okay, is the same. Okay, you will still get the same kind of explanation, except that the resistor will change lah. Okay, so let me show you the answer. Ta-da, this is the answer. So again, you can pause the video and and copy it down. So basically, when it is dark, the resistance of resistor X increases. Okay, no matter what position you put it in, the LDR works that way. When it is dark, when there's no light, resistance will increase. And because the resistance increase, the potential difference also increase and causes base current to flow. That's the flow that we want. Big potential difference causes the base current to flow. When the base current can flow, the transistor is switched on, and then after that, whatever it is, alarm, LED. In our case here, it's LED. Okay, so the keywords are the ones that are highlighted in yellow. The resistance needs to increase so that the potential difference can increase, so that the base current can flow, so that the transistor can be switched on, and so that whatever device that you have will light up or will make a sound or whatever it is. Okay, that particular order needs to be remembered that way. Okay, final question. Okay, diagram 4.1 shows the black body radiation curve. Okay, if you're my student this year, you will know why this question is so funny to me. Okay, but it's the different question. Okay, it's just that so black bodies are the ideal absorber and radiator. Okay, it's two things at one time. Okay, based on diagram 4.1, compare the total energy radiates on the left side and the peak of the peak to the right side. Okay, so if this is the peak over here, you're basically talking about compare the energy over here and the energy over here. Okay, the energy is calculated by the area under the graph lah. So obviously, the right side, sorry, the total energy, okay, on the right side is more than the left side. Basically, that's all I want. Okay, the right side is more than the left side. And so the reason for this is because the area under the graph, okay, of the right side is greater. Okay, very obviously greater, like you can see. Look at this under the graph over here and look at this side. Definitely you can see it's greater. Okay, diagram 4.2 shows the graph of kinetic energy. Now, different metals with different threshold frequencies and different work functions. Okay, so based on the graph on diagram 4.2, what is the inference that can be made about W and FO? Okay, so you can say that the work function and the threshold frequency really only depends on the type of metal. Okay, now I find this question particularly interesting because of the word inference. Okay, So whenever we talk about physics and we talk about inference, the key word for inference is depends on. Something depends on something. That's usually how an inference in physics SPM is made. Okay, so in this particular case, we find that the threshold frequency and the work function depends on what type of metal you use. That's the only thing that changes. Okay, the manipulated variable, okay, in that sense. All right, the work function is 5.81 times 10 to the power negative 19. The frequency given is 1 times 10 to the power 15. Okay, so calculate the threshold frequency. Again, we have the work function formula equals to the H times the threshold frequency. This is what we want to find. Okay, so 5.81 times 10 to the power negative 19 equals to 6.63 times 10 to the power negative 34 multiplied with the threshold frequency. You calculate, you get threshold frequency is 8.136 times 10 to the power of 14. Okay, hertz. I think it should be 14 though. Yeah, should be 14. Okay, and so calculate the maximum kinetic energy. Now that you have the work function, okay, you can calculate the maximum kinetic energy, which is, okay, so we come back to this, E equals to W plus kinetic energy. Okay, now you have the work function and you need to find this one lah. Okay, so let's talk about the frequency given. The frequency given is 1 times 10 to the power of 15. And so you know you can calculate the photon energy by using HF lah. Okay, equals to our work function is given as 5.81 times 10 to the power of 19. Sorry, negative 19. Okay, plus, then this is what we want to count, the kinetic energy. So HS is 6.63 times 10 to the power negative 34. Okay, the frequency is 1 times 10 to the power of 15. 1 power of 15 equals to 5.81 times 10 to the power negative 19 plus KE. Okay, you move it around, and you will get the kinetic energy equals to 8.2 times 10 to the power of 20 joules. All right, and there you have it. Okay, the end of this module. So I hope that this has helped all of you, okay, to answer this. I think we can see a certain pattern lah, okay, with this question 1 to 4. The most obvious one is usually around question 3 or 4, you need to expect an explanation question to come out. And usually questions 1 to 4 is where most of the calculation questions come out lah. If we look at the trend of these 6 papers alone, it seems that we may want to focus on gravitation and quantum for the first 4 questions lah. Okay, I hope this helps. I made this recording before Chinese New Year, so Happy New Year to everyone. Happy Chinese New Year to everyone. I will see you either in the next video or I will see you when I see you. All right, take care everyone.